So, hello everyone, how are you all? I hope you all are fine and safe. Well, again, welcome back to Quantum Mathematics. I'm Aman, just welcoming you all to a new amazing video in which we are gonna talk about further like the one video. It's maybe you can consider this video as the successive video of the one which was which took 50 minutes, right? I have recorded a video in which we have talked about the Riemann zeta of 1, right? Actually, this one, right? Let me just tell you why this video is the successive order of that video. So in that video, we have talked about this one, right? And that was quite crazy, I would say. And I know you guys are having a lot of questions regarding that, but I would say whatever I have done in that video, I have done on the basis of all things which I have learned and which I have proven myself by myself actually, right? So I think everything was correct. Everything. I never like any misused or I've never jumped off any steps in that video. So yeah, I think everything is correct in that video, right? So basically, in that video, we have talked about Riemann zeta of 1, right? Right. Okay. So basically, it came out to be something sort of like, as much as I can remember, it was, wait a second, Riemann zeta of 1 came out to be Euler-Mascheroni plus 1 over 2 ln phi plus 1 over 2 ln of 1 minus z squared and plus 1 over 2 here as well. The sum as n goes from 1 to infinity of I think it was 2, no, wait a second, yeah, I got it. Riemann zeta of 2n z to the 2n, and then we had minus 2 n ln of n, and then we had plus n ln of n plus 1 whole squared minus z squared and over n. So this was the thing that we had proved in that video, right? Okay, but in this video we ain't gonna talk about any Riemann zeta function, right? But as much as like, although I know that, but if you have watched this video actually in which we have talked about this, so you must have got that what things I have used actually, because in the beginning of that video I have explained you all the important and dominating stuffs that we are going to begin with, right? So basically it was the very first thing, that is this relation, that is phi z cotangent of phi z equals 1 minus 2 times the sum as n goes from 1 to infinity of Riemann zeta of 2n times z to the 2n. So this was the very first relation that we used actually, and we just began proving this one from here. But it's not the single thing that we have used. And the another one was the Weierstrass product, right? So it was something sort of 1 over gamma of z equals z times e to the Euler-Mascheroni times z and times the infinite product as n goes from 1 to infinity of 1 plus z over n e to the negative z over n. So this was the second thing that we maybe it wasn't the second most dominating actually, it was the third one, right? And the second one was Euler's reflection formula actually. So these things were the most dominating stuff, I would say. So it was something sort of gamma of 1 plus z times gamma of 1 minus z over pi equals, oh wait a second, z over sine phi z. So these three things we have used these three things to reach up to here, right? And yeah, that was a fantastic journey. The way we just incarnated the Riemann-Zitov one out of nowhere. So yeah, I will recommend you to watch that video till the end. That is having a lot of stuffs in it, right? But now, why I'm just saying that it's the successive order of that video, right? Basically, this one and this one would be same. We are going to use these two things, the Euler's reflection formula and the cotangent relation with the infinite sum of Riemann-Zitov even arguments, right? But we are not going to consider this Weierstrass product. We are going to consider the Euler's product actually. So you know what? We are having a lot of stuffs which represents gamma function, right? Like the Gaussian expression or the Gaussian product, the Weierstrass product, the Euler's product. So this video would be on Euler's product. Although, and you know what? Why I'm considering this? Because I have proven this recently. So that's why let's just talk about this one. And let's just check what we're gonna have out of this. And is it a Riemann-Zitov or something else? Wow. So basically it is gamma of z equals 1 over z times the product as n goes from 1 to infinity of, it was, wait a second, yeah, 1 plus 1 over n to the z and n over n plus z. So this is what it is actually, the Euler's product. And the rest of the things would be same, but I think till this step actually, well, I think I should consider just beginning our journey from this step here, because maybe you haven't watched that video. So if I'm just gonna consider you guys have watched that video, so I think, I'm not sure, so I think I should consider just explaining you from this scratch, right? Maybe it's gonna take time. Oh, obviously it's gonna take time. And yeah, we are having this much amount of thing. Okay, so now let's talk about this. So basically we have to use those three things to just check whether we gonna have ended up actually, because we used the Weierstrass product and we ended up like just evaluating the Riemann-Zitov one or the closed form of Riemann-Zitov one. But now let's check this. So let's talk about that equation, the very first equation. So we have pi z, cotangent of pi z equals 1 minus 2 times the infinite sum as n goes from 1 to infinity of Riemann-Zitov 2n z to the 2n. Okay, so let's isolate this sum here. So we can do that something sort of this. Adding both sides that sum and subtracting both sides this pi z cotangent of pi z simultaneously. So that's gonna be this sum 2 times this sum of Riemann-Zitov 2n times z to the 2n equals 1 minus pi z cotangent of pi z, right? And now isolating this sum is gonna give us this sum as n goes from 1 to infinity of Riemann-Zitov 2n z to the 2n equals 1 over 2 minus pi over 2 over, wait a second, z times cotangent of pi z. So this is what we are having after isolating this sum. And why I did that, because actually we are going to take the integral of this equation, but before that we have to divide both sides with z actually, in order to just get rid of this z here. And let's talk about this. So if we divide both sides with z in this equation, like we got the isolated part of this sum. So if we divide both sides with z, so it's gonna be z to the 2n over z. So that's gonna be z to the 2n minus 1, right? So basically this is gonna be z to the 2n minus 1. So this sum as n goes from 1 to infinity of Riemann-Zitov 2n and it's z to the 2n minus 1, right? And since we are dividing this part with z, So that's gonna be 1 over 2 over z, which is 1 over 2z, and it's gonna be pi z cotangent of pi z over 2 over z, which is gonna be pi z cotangent of pi z over 2c. So z cancels out, and we would be left with pi over 2 cotangent of pi z. So basically, it's 1 over 2z minus pi over 2 cotangent of pi z, right? And yeah, now our next step is integrating both sides with respect to z. So integrating both sides with respect to z here. So basically, if we take the integral of this sum, as n goes from, oh wait a second, it's not 0, it's 1. Riemann zeta of 2n z to the 2n minus 1 dz equals, well, since we are having two separate functions on the right hand side, so we can just split the integral into different integrals actually. So basically the first one is going to be integral half times the integral of 1 over z dz actually, and minus pi over 2 integral of cotangent of pi z dz. I hope you guys are just clear with that. Let me just check. I think it's visible there, but it's all right. I'll just copy that down over here as well. Don't worry. So yeah. So we have the integral of the sum as n goes from 1 to infinity of Riemann zeta of 2n z to the 2n minus 1 actually, don't worry, don't just forget about that. So z to the 2n minus 1, and it's 1 over 2 integral of 1 over z dz, and minus pi over 2 integral of cotangent of pi z dz. Okay, now let's talk about the integral of cotangent of pi z, because since we know about this integral actually, it's just ln of z, or the next step could be the sum. Due to linearity, we can just switch up the order of the sum, and it's Riemann zeta of 2n integral z to the 2n minus 1 dz, the basic integral, whom proof I have uploaded on my YouTube channel. Like the integral of x to the n is x to the n plus 1 over n plus 1. So you can consider watching that as well. That's interesting. 1 over 2 ln z, and minus pi over 2 1 over pi ln sine pi z. Now you would say, Aman, what have you written there? You cannot just jump off steps. Dude, don't worry, I'm not jumping off steps. Let me just explain you. So we have the integral of cotangent of pi z dz. This can be written as cosine of pi z over sine of pi z. And when you plug pi z equals t, and you have the derivative of the denominator in the numerator, so that's gonna be ln of the denominator. And because we are having pi z over there, so we would be getting 1 over pi and ln of the denominator. So it's ln of sine of c. So yeah, this is what you are having, right? Yeah, that's cool. And I'm not going to prove the integral of 1 over z is ln z. Okay. So yeah, we are having that much amount of thing actually. And well, we haven't just solved this yet. So that's going to be z to the n, z to the 2n over 2n, right? So the integral of this one actually. So basically we are having the sum as n goes from 1 to infinity of Riemann zeta of 2n z to the 2n over 2n equals 1 over 2 ln of z, and we got rid of this pi term, so actually it's 1 over 2 ln of sine pi z. And both the sides, like we're having 1 over 2 as a factor, so we just got rid of that as well. And finally we are here with our first result, and which we have to note down. And soon we will introduce the Euler's reflection formula, and then after we will introduce the Euler's formula, actually Euler's expression. So yeah, so this is the sum as n goes from 1 to infinity of Riemann zeta of 2n z to the 2n over n, right? So this is ln of z minus ln of sine phi z, and we can write ln of z minus ln of sine phi z as ln of z over sine phi z, right? Property of logarithm, a natural logarithm actually. So it's Riemann zeta of 2n z to the 2n over n equals ln of z over sine phi z, right? And this is your final result for now actually, for that instant. And now we are going to introduce the Euler's reflection formula. So we are having, I have proved this down as well. I think couple of videos I have uploaded of the proof of this one actually. Euler's reflection formula. So this is amazing. Like look, this is the gamma of z times gamma of 1 minus z equals pi over sine pi z. But we are having z over sine pi z, so we are just gonna multiply both sides with z, right? So that's gonna be z times z, and dividing both sides with pi. So that's we're gonna get rid of that as well. And you know what? Z times gamma of z is gamma of 1 plus z. That's why I have written this Euler's reflection formula in terms of this one, right? Gamma of 1 plus z. Although in the beginning of the video, but although the exact Euler's reflection formula is gamma of z times gamma of 1 minus z. Gamma of z times gamma of 1 minus z equals pi over sine pi z, right? But yeah, due to some like after some manipulations and playing around with gamma function, we are just having this much things. And now we are having here ln of z over sine pi z. So basically we have to take natural logarithm both sides, and we would be just having, wait a second, I shouldn't be just saying all the stuff. Okay, so this is what it is. So we are taking natural logarithm actually. Taking natural logarithm. So when you take the natural logarithm over there, so it's ln of gamma of 1 plus z times gamma of 1 minus z over pi equals ln of z over sine pi z, right? Yeah. And then we can again apply the same result that we had applied here for this one actually. We have to go from here to here actually. So that's gonna be ln of gamma of 1 plus z times gamma of 1 minus z minus ln pi equals this result. And this result is eventually equals to this sum. So we can write this as and this equation to be noted, I would say. Very important equation. I'm gonna just copy that down here. So we are having ln of gamma of 1 plus z times gamma of 1 minus z minus ln pi equals the sum. Euler's mass. Oh, sorry. I'm sorry. Riemann zeta function z to the 2n over n. And now we have to look for the left hand side of this equation, right? Yeah. Since ln pi is a constant, so we would not be bothering that. We would not be disturbing that, but we would be just playing around with this. And how? The way we did that in the previous video with Weierstrass product, we are gonna use the Euler's product here. So this is how, like, wow, amazing. So yeah, we are having some sort of Euler's formula actually. Let me just use another chalk actually. I'm just dying with chalks. Oh, come on. Give it to me, dude. Yeah. So, okay. So now we have Euler's product. Okay. Yeah. So basically Euler's product is, as I have explained you earlier as well, it's gamma of z equals 1 over z times the product, and it's basically 1 plus 1 over n whole to the z, n over n plus z. And you know what? We want gamma of 1 plus z, gamma of 1 minus z. So let's just replace z with 1 minus z once, and then with 1 plus z. So firstly, let's talk about gamma of 1 minus z, or let's talk about gamma of 1 plus z anyways. So you have to replace all the z's here with 1 plus z. So 1 over 1 plus z times the product, and it's 1 plus 1 over n whole to the 1 plus z, and n over n plus 1 plus z. So this is your first equation. Actually, first expression I would say. And now let's talk about the second one, when we replace z with 1 minus z. And then we just have to multiply both the equations. So if we talk about gamma of 1 minus z, so it's 1 over 1 minus z times the product, and it's 1 plus 1 over n whole to the 1 minus z, and n over n plus 1 minus z. Now multiply gamma of 1 plus z and, oh wait a second, why it is that? Gamma of 1 minus z. So if we talk about gamma of 1 plus z times gamma of 1 minus z, so that's gonna be 1 over 1 plus z times the product, as n goes from 1 to infinity, of 1 plus 1 over n whole to the 1 plus z, and n over n plus 1 plus z, right? And the parenthesis outside there as well. And the times, we are having 1 over 1 minus z times the product, and it's 1 plus 1 over n whole to the 1 minus z, and n over n plus 1 minus z. So this is what we are having so far. And now we are just going to multiply these results actually. The first, like this term with this one, and the arguments of the product with the arguments of the another product, because eventually they are going from n equals 1 to infinity, so we would be considering just multiplying the terms, arguments, and using a single product, that is n is going from 1 to infinity. So let's just talk about that. So when we multiply the front terms actually, so 1 over 1 plus z times 1 over 1 minus z is gonna be 1 over 1 plus z times 1 minus z, which is 1 minus z squared, right? So basically gamma of 1 plus z times gamma of 1 minus z is coming out to be 1 over 1 minus z squared from this front terms actually, and times the single product as n goes from 1 to infinity, and this is gonna be, well, we can write this as 1 plus 1 over n and times 1 plus 1 over, wait a second, n whole to the z, right? We can just factor something like this, actually this term. And if we talk about that one, so it's 1 plus 1 over n times 1 plus 1 over n whole to the negative z, right? We can just do that, and we are left with these two terms. So n times n is n squared over n plus 1 plus z times n plus 1 minus z, right? So basically, if we consider these two like factors, so that's gonna be n plus 1 whole squared minus z squared, because if we consider n plus 1 equals a and z equals b, so it's a plus b and a minus b. So basically, it's gonna be a squared minus b squared, which is n plus 1 whole squared minus z squared. And if we talk about this one, so this is exponents as a positive z, and we have the same thing as exponents with negative z. So they are gonna cancel out with each other. That's amazing. So again, we are having gamma of 1 plus z times gamma of 1 minus z equals 1 over 1 minus z squared, and times the product. Since 1 plus 1 over n times 1 plus 1 over n, so it's gonna be n equals to 1 to infinity. 1 plus 1 over n whole squared, right? And the last term is n squared over n plus 1 whole squared minus z squared. So this is what we are having so far. Wow. And now it's not end yet. We have to take the natural logarithm of that equation, actually this equation. So we would be just having this part, and then we have to subtract both sides with negative natural logarithm of pi, and we would be just getting the stuffs that equals to this sum. So yeah, this is how we should this is how we're gonna do that actually. Okay, so now let's just consider taking the natural logarithm, and you have to be cautious here. So taking natural logarithm, right? So that's gonna be ln gamma of 1 plus z times gamma of 1 minus z equals ln of that chunk of things actually. So it's 1 over 1 minus z squared times the product, and it's 1 plus 1 over n whole squared, and we are having n squared over n plus 1 whole squared minus z squared. Okay, now before just introducing this natural logarithm inside this parenthesis, let's just talk about this argument. So basically it is gonna be ln of 1 over 1 minus z squared times the product. Well, we can write this as n plus 1 over n whole squared, right? And basically we can just split this into two parts. So it's n squared and n plus 1 whole squared, right? Right. And why I'm doing that? Because we are having a factor of n squared in the numerator. So we are just gonna get rid of that. So this n squared cancels out, and we are just getting left with n plus 1 whole squared over n plus 1 whole squared minus z squared. Okay. And now we are good to go with the natural logarithm inside this parenthesis. So this is crazy, right? Okay, so we have the natural logarithm of gamma of 1 plus z times gamma of 1 minus z equals, it's gonna be, because ln of, we can do ln of this part, so it's gonna be negative of ln of this denominator. So it's negative 1 minus z squared and times this, so it's plus ln of this product. Eventually that's gonna be an infinite sum. It's n plus 1 whole squared over n plus 1 whole squared minus z squared. Okay. So again, ln of gamma of 1 plus z times gamma of 1 minus z is gonna be negative ln 1 minus z squared, and then plus the sum as n goes from 1 to infinity of natural logarithm of this argument. So it's n plus 1 whole squared over n plus 1 whole squared minus z squared, right? So this is what we're having so far, and now we are gonna consider just writing this in terms of a rule actually of natural logarithm, which is ln of a over b is ln of a minus ln of b, which we have used actually in this video actually 2 times, right? So let's just use that and let's just expand this a little bit. and actually we have to subtract both sides with natural logarithm of pi, and yeah, so yeah, we are having natural logarithm of gamma of 1, wait a second, 1 plus z times gamma of 1 minus z equals negative ln of 1 minus z square, and plus the sum as n is going from 1 to infinity of ln of n plus 1 whole squared and minus ln of n plus 1 whole squared minus c squared. So that's gonna be 2 times ln of n plus 1 actually, because the exponents is gonna be in front, right? Okay, and let's just adding both sides. Negative ln pi. So it's ln of gamma of 1 plus z times gamma of 1 minus z minus ln pi equals minus ln pi, let's write it down, and minus ln of 1 minus z squared, right? And then this infinite sum. So it's the sum as n is going from 1 to infinity, 2 times natural logarithm of n plus 1 minus natural logarithm of n plus 1 whole squared minus z squared. And this is the result actually, which is eventually gonna equal to this infinite sum. Whoa, we are here, guys. We have reached. I did that, dude. I did that. Okay, so from these two equations, we can say that the sum as n goes from 1 to infinity of Riemann zeta of 2n z to the 2n over n equals negative ln pi, negative ln of 1 minus z squared, and then plus the sum as n is going from 1 to infinity of 2 times of natural logarithm of n plus 1 minus natural logarithm of n plus 1 whole squared minus z squared, and this is your final result. So here we are not having any sort of Riemann zeta function, like any specific value, like unlike we did in the previous video actually. And we can just make it looking quite better by just adding both sides with these two sums. So maybe that's gonna be quite good looking, because this negative is like bothering us, but it's all right. So basically adding both sides ln pi and ln of 1 minus c squared. So it's ln pi plus ln of 1 minus z squared plus this sum as n goes from 1 to infinity of Riemann zeta of 2n z to the 2n over n equals this sum actually. So sum as n goes from 1 to infinity, 2 times natural logarithm of n plus 1 minus natural logarithm of n plus 1 whole squared minus z squared. And here we are with our final and most final result. So I'm not sure whether we can go further with this, but yeah, if I got to know about something, we can go further in this equation. So yeah, obviously I'm just gonna tell you that, right? But for now, consider this equation and let's just leave it now because it is a lot of things, right? And I think this thing is crazy. The way we use the Weierstrass product and the way we use here the Euler's product, everything was crazy. Everything was like, it was diving into mathematics, deep. Again, guys, I think it's fine, and everything was good. Everything we did, and I think I have never made any kind of mistake in the whole process that I have solved so far, and even I have solved this by myself personally. So I think the result is, I'm sure that the result is same the way I solved it firstly or maybe secondly, and this time is also the same result actually. So everything just went so far and everything just went so correct, and now I would take leave here, And again, guys, if you got to learn something from this video, just make sure to like, subscribe and share. And if you have any kind of doubt so far, you're free to ask me in the comment section. I'll be there to just reply over your questions. Goodbye, guys. Take care. Love you. And it's 35 minutes. Goodbye, guys. I'm just waiting for that. Okay, here it is.